So welcome back. So in the last class we understood what is the link, joint and DH parameters, and we did DH parameter table for at least one of the example, that is 2 degrees of freedom robot. So in continuing further with that, so let us do some more examples of spatial robots now. So spatial robots are robots which can position themselves in space, Cartesian space, in XYZ location, anywhere in space. It may have some arrangement later on as an attachment like a spherical wrist, or maybe just a plunger or something like a tool, some other tool, maybe a parallel robot mounted on top of serial robot, so that it can do further orientation manipulation. Okay, so let us begin. Yes, let us just recall the steps to assign DH parameters. So you see, you need not to mug it up, just you may just take a snapshot of this. Okay, so yes, you also should recall DH link transformation matrix AI minus 1 I. Okay, so let us move ahead quickly to the example. So here is one 3 degree of freedom cylindrical robot. So let me just show you a small video to make you recall
or whoever sets it up.
How does it work. So this is how it was. So you see the arm which is horizontal to the ground can extend its length, right? It can extend its length, okay, and it can rotate about a vertical axis. Okay. Let us quickly do this one. So this is your cylindrical robot kinematic representation. So this is your first degree of freedom, that was at the ground up. Okay, so this is to rotate whole of the two prismatic joints. One is here, other one is can change the radius of this. Okay, this arm point can move backward and forth, back and forth in this direction. Okay, so and this can move like this up and down. Okay, so there is some minimum height to which it can come, and there is some maximum height to which it can go. Okay, so quickly we can place z axes along the motion axes. So that is the first thing you should do, that is choose zi as axis for rotation or translation. So even if it is rotation axis, so quickly we can put the first axis like this. Here is your one, this is your first axis, that becomes your z0. Okay, and then you have another one, yet another one which is here. Okay, this is your z1. Okay, this is your z1, and then the third one is here, which is like this. Okay, so this is your z2. Okay, so from 0 to 1, 1 to 2, and 2 to 3. So it requires total 4 frame placement. One is which is permanently attached to the ground, that is 0 0 0, x0, y0 and z0, that is not rotating, that is the fixed frame about which first link rotates. So now put other parameters as such. So other parameters are, we need to put xi as common normal to zi minus 1 and zi. This is one of the step of placing DH parameters. Okay, first place the frames and then we'll assign the parameters. So xi is to be put, xi is common normal to zi minus 1 and zi. Let us look the first link, okay, which rotates about the ground. So z0 and z1 is here, z0 and z1 is here, as because there is no distance between them, both the axes are along same axis. Okay, so you can draw a common normal anyway, so it is convenient to put common normal in the original direction where your x0 is. Okay, as over here. Okay, so I will quickly put it as common normal like this. This is your x1 also. Got it? This is your x1. Okay, so this is z0, this is z1, common normal to that is x1. Okay, now let us put, this is your Z2, this was your Z2 and this is your Z1. Okay, this was your Z1. So Z1 and Z2, again common normal to them, it is X2. So this becomes your X2. Got it? And then this Z2 finally terminates over here, aligning with Z3. Z3 is just a dislocation of second frame to the new location, that is third frame. Okay, that is O3. That is their end effector frame as well. Got it? So now put the constants AI and alpha I. What is AI? AI is the distance between two Z axes, that is the link length, and alpha is nothing but a link twist. So you see there is no angle between Z0 and Z1, both are aligned in a single axis. Okay, so there is no link twist. So Z and Z, there is no angle between them that can be measured along x axis. So alpha 1 becomes equal to 0. Then talking about alpha 2, Z1 to Z2, you see there is some angle. So if this is your Z1, this is your Z1, this is your Z2. Okay, so you have to rotate clockwise in order to align with Z2. So it is alpha 2 is equal to minus 90 degree. Then is your alpha 3. Again Z2 and Z3 are aligned together. So alpha 3 is equal to 0. Now let us see what are the link lengths. So link lengths are distance between Zi minus 1 and Zi measured along xi. Let us see if it is there. So Z0 and Z1, they are aligned. There is no distance between them. Z1 and Z2, again there is no distance between them, they are intersecting at this point. And similarly Z2 and Z3, they are along the same line. So again A3 is also equal to 0. So A1, A2 and A3 all are equal to 0. Okay, so you have assigned alpha and A. Now moving ahead, so what is theta I and di? So you see carefully here, theta 1 is there because that is the joint variable for the first link. Okay, so first link rotates with theta 1 with respect to the frame O0 that is attached to the ground. So theta 1 exists, whereas there is no theta 2, there is no theta 3, that is not there, that is not there. Got it? Now just see if D's are there. So D is nothing but joint offset. So that is the distance measured along Z axis between x0, x1, x1, x2, x2, x3 like that. Okay. So D1 is there, you see, from it is the distance measured from O0 to O1, that is frame 1. So this is your D1. So that exists, that is having a length of D1. Now what is D2? It is again distance between measured along Z. So it is here. So D2 is here, but as because it is a prismatic joint, so D2 is a joint variable. D2 is a joint variable. Now this one, this is your D3, that is measured along Z2 between two axes, x axes. Okay, so this is D3. So D3 is again it is a prismatic joint, so it is a joint variable. Got it? So these are the parameters. Now let us put all of them together in the table form. So this is your DH parameter table. I have marked joint variables as theta 1, D2 and D3. If you remember your DH parameter link transformation matrix, this one, okay, you have to use this one every time. So yes, let us just quickly go to that page. So if I can substitute my DH parameter values to link transformation matrix, I will get A01, A12, A23 like this. You can try doing it yourself, and concatenating all of them together, taking product of them together, you get the forward kinematic transformation matrix 4 cross 4 homogeneous transformation matrix like this. Okay, so this is it. So this is your forward kinematic transformation matrix. This shows the end effector position. This shows your end effector orientation. Okay, so can we compare any of these? So quickly, at least this one you can understand. If you can see your previous figure, so this is your, how much was that? So you, if you remember, it was d1 plus d2. Z is d1 plus d2. So if this is d1, this is d2. So perpendicular distance along z, this was your y, this is your x, and this is your z. So total perpendicular distance is along z is d1 plus d2. Coming to x and y, can we do that as well? So this is your d3, okay, and that rotates about vertical axis by an angle theta 1, you see, that is theta 1. So how much will be that? So x, along x, if you take projection of d3 looking from the top, so this is your y, this is your x, okay. So your link d3 goes like this, this is your angle theta 1. So this point coordinate, x coordinate will be minus d3 sine theta 1, okay. Now how much it will be your y coordinate? It will be d3 cosine theta 1. Got it? So these are the three which we can quickly verify. This is not that trivial in many robots, but yes, at least for this one you can quickly verify. Now can you do orientation verification also? So what was that? So it is projection of the UVW frame. Over here it is V and UVW frame along X, Y and Z. So can you do that as well? So projection of X along X, projection of X along Y, projection of X along Z. Okay, so you can quickly understand if this rotates your this axis x3 rotates by an angle theta 1, so you can quickly find out. So along x will be x3 cos theta 1. So x3, if it is the unit vector, it is simply cos theta 1. Similarly along y it will be x3 sin theta 1. Along z it will be 0. So you see, this is your unit vector, column vector, first column of the transformation matrix. Similarly you can work out for other matrices. Y axis projection you can quickly find out. So this projection along x will be 0, along y will be 0, but along z it will be, because it is pointing downwards, it should be 0, 0 and minus 1. Okay, so that is how it can be worked out. So if you see it here, so it is cos sine 0, 0, 0, minus 1, and similarly this one. So these are the three projection, you got it. So this is your orientation matrix, that basically is orientation of the end effector frame, and this is position of the end effector frame. So this is how forward kinematics can be interpreted. Okay, so now let us do one more example that is very important, because most of the industrial robots are fitted with this kind of joint. So let us first make you understand how does it look like. Okay, I will just switch a virtual robot that I have it here. So this is it. So you see, you can move it. So first axis was something like vertical axis. If you can see it here, this was your vertical axis which is fitted here. So first axis can make it go like this, okay, and the second axis can make it do this, third axis can make it do like this. So forget about first three, what is the last three? Okay, can we do it as well? So yes, so this is your fourth axis which can rotate whole of the wrist center point like this. So where is your wrist center point? It is the point which is somewhere over here inside center line. Okay, So it does it. Okay, so this is your axis 4, this is your axis 5 again, that is also coming, meeting it at a same wrist center point, and then the last axis. In order to show this, let me make it like this. Okay, if you can see it clearly, you see the last axis is now rotating, that the black dial one, that is the tool post on which tools are mounted. Any robot gripper is mounted, welding tool is mounted. Okay, so that is the flange with some holes, standard holes, so that you can mount it. So this is it. So you see axes are all intersecting. Axis 4 is intersecting at the wrist center point somewhere over here. Axis 5 is also crossing that one only along this, and axis 6 is also very similar. Okay, so let me just show you axis 6 once again. So this is your axis 6. So that axis is also, if you protrude it backward, so that also intersects at the same location. So hope you got it. So let me just switch it off and let us come to the kinematic picture of that. So here it is. The first frame that is visible out here is a part of the last frame of most of the 3 degree of freedom positioning robot. So this is the orientation part of it. Okay, so this spherical wrist basically gives you the orientation. The first 3 gives you the position. So let us begin with placing the z axis first. So this one, this is the part of the last frame of a 3 degree of freedom system, positioning system. So this is your last frame of that 3 DoF system. So this is your Z3. Got it? So that is coming to the wrist center point. Now let us put the another cross axis which is there. So this is the second one for this one. So this is your Z4. If you remember your cylindrical robot that we did just now, so that had a final axis. So first one was like this, Z0, then Z1, then you had Z2, and finally you had Z3, that was like this. Got it? So that from there I am establishing this spherical wrist. So this is your Z3, then your Z4, and finally you will have Z5. So here goes your 6th link that finally ends here. So this is your 5th axis that rotates the 6th link, and 6th link at its end, it has a 6th frame, that is Z6. It is nothing but a dislocation of the axis which is here, 5th axis, exactly that comes here, and there is a distance between these two. So this is your spherical wrist center, and finally this is the distance D6 because it is traveling along Z axis. So it is D6 that finally ends here. So this is your last frame, that is the tool frame. Okay. Normally they are 4th, 5th and 6th axis. So you can put it like this, this and this, or in order to do it work conveniently, here theta 1, theta 2 and theta 3 is equally good. So if I put it all over here, so using this DH parameter I can quickly get this table. Got it? So this is exactly the same. So there is no AI because all the link axes are intersecting, all the joint axes are intersecting. Okay, if they are intersecting, there is no distance between them, so link lengths are 0. Okay, and also D1 and D2 is 0. Okay, because distance traveled along Z axis is also 0. Only distance that you see here is the last one, that is D3, which is here, or you call it D6, they are equivalent, okay, for convenience. So this is D3. So this is D3, that is actually collocating from this point to this point. So it is just making some offset along that line. Okay, so that is your final thing. And theta 1, 2, 3 are joint variables. If you can measure angle alpha, that is the twist angle, that is angle rotated about x axis from previous z to the new z. Okay, so that is there. So if you do it, you will get minus 90, 90 and 0. Okay, so this is how your DH parameter table can be worked out for this. So first transformation, link transformation matrix goes like this. Second and third one are here. If you take product of all of those, you get forward kinematic transformation for this spherical wrist. Got it? So this can be attached on top of any robot. Okay, so first 3 axes will do its job, whereas this 3 will go as 4, 5 and 6 number on top of this. Instead of putting 1, 2, 3 the way it is here, it is just 4, 5 and 6 and they are equivalent. Okay, so 1, 2, 3 for first 3 joint of the robot, 4, 5, 6 for the spherical wrist. Okay, so now can we do it here? This is what we did it here. So immediately, if you can recall, this is your same old robot, the one which you have worked out just now. Okay, this was not included there, so you ended maybe somewhere over here. That was your last joint. Okay, last point. Okay, end effector point. Now you have attached 4, 5 and 6, all the 3 intersecting axes. So over here it is shown like this. There may be an instance when you see it can be made exactly like this. So this is all axes. Now axis 4 and 5 are collinear. Got it? So it becomes like this approximately. Okay, so you got it. So this is how it is drawn over here. So it is axis 4, this is axis 5, this is axis 6. Got it? So spherical kinematic transformation matrix that you obtained in the previous slide and the forward kinematic transformation matrix that you obtained for cylindrical robot earlier in example 2. Okay, you can take product of both of them. So effectively you will get this. Finally you will get this, and this is your thing. This you can work out using any symbolic mathematics computation tool, and you can arrive to this result. Got it? Okay, so now let us do one very popular robot that is known as SCARA robot. So let us just look at it. How does it look like? Okay. So this robot is known as Selective Compliance Assembly Robot Arm. This is a Fanuc one. There are many Omron companies making it, many other companies also they are making it. So hope you got it. It has first three axes which are there. First one was revolute axis. First vertical one is a revolute axis. You have still another one, that is revolute axis, and the final prismatic one is there, that is making whole of this go up and down, as well as it can orient about its own axis. Now it is working. So you got it? Okay. So now let us again come back to the original kinematic picture of this, although it looks quite boring here, but you see this is very important in order to put DH and do forward kinematics here. So let us quickly do that. So you have first axis which was the vertical one, that is Z0, which is shown here. Ground frame I have kept exactly like this is my forward, this is my other side of it, Y0, X0 and Z0, about which first link is rotating. Okay, so this is the shape of your first link. If you can see this one, this is your first link. Here is your second joint. Okay, so this is your Z1. Okay, so first link rotates about Z0. You have cylindrical joint which is here. So this is your Z0. This is your Z0, about which whole of this is rotating, this yellow one that I have marked here. Okay, and Z1 moves along in circular way. Okay, so this is your Z1. Okay, again that is extended further, and you have a point here about which there was a prismatic joint that can go up and down. So this is your Z2. This is your Z2. I am placing all the Z's now. Okay, and this can go up and down, make a point which is end effector point, and this has an frame which is put here, that is the fourth frame. Before to that there is an intermediate frame that was able to rotate whole of this along vertical axis. Okay, so this is your cylindrical joint. So this is your Z3. So you got it. So you have Z3 and Z4 both are aligned together. Okay, so it originates from here. This one originates from here. Z3, O3 is here, whereas O4 is here. This is your O0, and you have O1 here, O2 here. Got it? And then you have to find out all the D's, that is the joint offsets. Okay, so what are the offset? So 4 degrees of freedom, it requires 5 frame. So let me just quickly find out all the offsets here. So going from x0 to x1 along z axis will be your offset. So this becomes your D1. So that is D1. Okay, and going from z0 to z1 along x1, so that is your A1. Okay, and both the z, there is no angle between them, so there is no twist, so it is 0. Theta 1 is the joint variable which is here. Got it? Hope you obtained it. Hope you got it. Okay, now let us come to yet another one, that is the second link. So you see quickly here. So this is your A2, that is distance between Z1 and Z2. Got it? And both are facing opposite to each other. So angle between them, this is the link twist measured about x2. So it is 180 degree, and there is no distance that is travelled along z axis. Okay, so this point and this point, they are moved along x axis but not along z axis. So that makes this link offset as 0, and theta 2 is the joint variable. Okay, now let us see the third one. So you see again you have link length that is equal to 0. Why? Again there is no distance which is measured between Z2 and Z3. Both are aligned together, so that is making it 0. Both are aligned, so twist is also 0, and it is travelling from O2 to O3 by a distance D3, that is the extension of that prismatic link. So this is the joint variable. Okay, and there is no rotation angle variable. Got it? So this is it. This is your third, and then the final one, let us quickly do it again. So now your fourth frame which is here, this is O4. Okay, this was your O3. So again there is no distance measured along Z3 and Z4, both are aligned together, link length is 0. Okay, there is no angle between them measured along x axis, so there is no link twist, so it is 0. Again there is some distance which is between them, that is D4. So that is basically the offset which is from O3 to O4 measured along Z, that is there. And finally this is a revolute joint, so that is a variable, theta 4 is the variable. So this is how this parameter table is put. Okay, and if you can find out all the individual link transformation matrices, all the 4, okay, using the link transform homogeneous transformation matrix I minus 1 I that we have just seen in the first recapitulation slide. Okay, I showed you. So you can use the same thing here and you can do it. And now you need to take product in order to find out the forward kinematic homogeneous transformation matrix. Okay, so this is your thing. So this represents again your position, this represents your orientation. 3 cross 3 represents your orientation. At least few of them you can quickly verify if you have obtained it correctly or not. So you see it is A1 C1 A2 C12. C12 means C cos of theta 1 plus theta 2. Okay, I use this as a shortcut to write it here, so that in a compact notation you can write it here. Similarly, C1 is cos of theta 1, got it? So that is what is written here, and same way I have put the signage also. So now if you can see it from the top, so this was the thing. So this was your link length, this is your A1, this is your A2. First one was able to rotate by an angle theta 1, this was by an angle theta 2. So looking from the top, it is very much like a two link robot as we have worked out earlier. So it is theta 1, this is theta 2, this is A1, this is A2. So whatever is this point has xy coordinate, so exactly same xy will be for the bottom one also, because it is just traveling vertically up and down. So whatever is the xy which comes here, same is the xy for this one also, so the fourth point also, got it? So it is just like a 2 degree of freedom robot now. So x will be A1 cos theta 1 plus A2 cos theta 1 plus theta 2. Similarly, y will be A1 sin theta 1 plus A2 sin theta 1 plus theta 2. So that is what is visible here. Okay. Now look at your vertical distance. So vertically you see you have traveled like this. So you went up like D1, and then you came down by D3 and you came further down by D4, got it? So total vertical travel will be D1 minus D3 minus D4. So that is what is visible here, got it? So at least the position thing you can quickly obtain. Okay, we can do for this also we can understand. It shows the final z axis, z4 is pointing downwards along z axis. So that is what here. So you see z4 is pointing downwards. So it has component along x, along y as 0, whereas component along global z, z0, z4, you see they are oppositely directed. So z4 have a -1 projection along z0. So that is what is here. So you see you can verify other elements are, because it was 2 DoF kind of thing. So orientation is something like this, got it? So this is how you can further cross check it. So this is your SCARA, which is a very popular industrial robot which is used for PCB manufacturing and those. Okay, so that's all for this lecture. So we'll be doing further forward kinematics, one full class for 6 degree of freedom industrial robot arm. We'll see various industrial arms also, which are very much similar to the one which we will be dealing with. Okay, so that's all for this lecture. Thanks a lot.